High deposition rate additive manufacturing processes, such as wire arc additive manufacturing or WAM, are important for aerospace industries due to their short lead times and unrestricted build size envelopes, enabling large parts to rapidly go from the design stage to completion, and there are also intrinsic cost and energy savings. Direct energy deposition processes also have the ability to build parts with site-specific properties by changing deposition conditions or the deposited alloy at any given region. Such parts would be impossible to produce using conventional processes such as casting, forging, or machining. Site-specific property design is particularly important to aerospace as it allows removal of detrimental component joints and can maximize weight saving. However, in WAM, due to the large remelt depth required to limit porosity and ensure high-quality parts with the layer-by-layer process, creating alloy-to-alloy transitions in situ by switching the wire feed for site-specific properties creates a large transition region with varied chemistry. In this region, the layer-by-layer deposition strategy creates a stepwise, exponential transition between the dissimilar alloys, rather than a sharp change in chemistry. Liquid mixing is often incomplete within these steps too. As a result, the microstructures and micromechanical behaviour can be quite varied in these areas. To investigate this microstructure variance and liquid chemical mixing, we recently studied an alloy-alloy composite build with two titanium alloys. Ti-6-4, the most commonly used titanium aerospace alloy, which has good strength and high damage tolerance, and Ti-553, a more specialised high-strength alloy. We deposited these alloys, one atop the other, with WAM in both orders. In these optical macrographs of the etched samples, the transition regions can be seen in the central areas through the contrast change. We measured the chemical mixing in these areas using electron probe microanalysis, and this plot of the elements as a function of distance shows the stepwise chemical mixing that results from the layer-by-layer deposition technique. Within each step, you can also see some local variance in the alloy composition, where the liquid has failed to completely mix during deposition. In titanium alloys, such as those used in this study, the microstructure consists of the hexagonal alpha phase and the cubic beta phase, woven together on a nanometer scale. The scale of this interweaving determines the mechanical properties. In particular, a finer microstructure results in a higher yield stress of the material. And, since the balance of the two phases is determined by the alloy chemistry, the stepwise alloy mixing in the alloy-alloy composite transition region produces abrupt changes in the microstructure. These electron backscatter diffraction orientation maps show the individual beta and alpha phases when the Ti-553 is transitioned into Ti-6-4 and vice versa. In the latter alpha phase map on the far right, in the first microstructure transition step, that is, the first layer deposited after the wire feed was switched to Ti-553, a series of heterogeneous parallel alpha lats were able to grow uncontrolled into the matrix of the Ti-553 due to the sudden change in alpha-beta phase stability. As deposition continues, the microstructure changes in a stepwise fashion for the next 2 to 3 layers until the nominal Ti-553 composition is reached, as shown in these backscatter electron micrographs. In contrast, when transitioning from Ti-553 to Ti-6-4, a very different microstructure gradient is found. This research was recently published in the Journal of Materials Characterization, and a link to the paper is provided in the video description below. This alloy-alloy composite deposition technique offers exciting opportunities for superior component design, but it's important to determine how the heterogeneous microstructures affect the mechanical properties across the alloy transition regions. Going forwards, we intend to take a close look at the micromechanical behaviour in the transition regions and continue to investigate site-specific properties using different alloy and material combinations.